Okay, so this is the part 3 of the mean variance portfolio optimization. It's a very important area of applications of optimization, especially the Kuhn-Tucker theory. So, if I do not allow short selling, then I just recall that my problem was of this form. Sorry, W. Here the mathematics actually becomes very difficult. What essentially is the Lagrangian in this case? And you have to take into account of the inequality constraints, n inequality constraints. So, your constraints have increased from 2 to n plus 2. So, there is a huge jump in the number of constraints. And in this case, writing the optimality condition is slightly non-trivial, because your Lagrangian would now have these Lagrangian parameters, and also would have a parameter which can for the moment let me write it as some theta 1 to theta n, and this theta 1 to theta n, these Lagrangian would be associated with these n non-negativity restrictions, and then this Lagrangian in this case would become plus theta I minus omega I, because I will write it in the form of less than equal to 0. So, that is your Lagrangian function now. So, you have changed the Lagrangian function. Your KKT conditions for this particular case, the KKT conditions for this particular case now becomes much more difficult. So, you have to first figure out what is the W which is giving you and so this is the one no short selling one. So, once you do not allow short selling, a problem actually becomes very difficult. You really need a machine to solve it. Once the data are given, you cannot solve it by hand even for small cases. It is not so easy doing this. Number 2, of course, you have to have this r hat omega equal to rho naught. Number 3, you have to have this as 1. Number 4, you have to be sure that these multipliers theta 1 to theta n, these are all greater than equal to 0. Also, you have to be sure that And further, there is another condition that would come, which we don't write here as a complementary slackness condition, that theta I rho I equal to 0 for all I. So solving this system of equalities and inequalities is not a trivial matter. Even for the previous case, uncorrelated case, the whole optimality condition would actually change, right? So it will whole system would actually change. So I would suggest you to really go ahead and try out for the problem that we had just solved. So if it is with short selling, how would I actually go ahead and do that? So it could be an exercise. For example, now if you want to take the gradient at W, so what I'll get is the following. So here I'll get the vector theta back, so which is theta 1, theta 2, theta n, and that would be equal to 0. So if you look into what we have done in the last one, so what we are having is, so if I write it down, even with those uncorrelated assets, so if I go to the previous example in the last class, then what I will have, for example, the first equation I will have is lambda 1 minus lambda 2 minus theta 1. So you have to have this, and you also should have theta 1 W1 equal to 0. So that is the way you are really going to figure out the stuff. So it's not so trivial to figure this thing out, and we won't have really time to figure out the details. If there is the details, I'll hand it over to the student TAs with the solution of this for this particular example from Leuenberger. And I would also ask students who are listening to this course to remind me that if I have forgotten to put solution of this, or at least show you how to analyze this situation. So once that is done, let us now go into more looking at the problem more deeply, right? So we'll go, and first we will take the two problems. The one which I maximize the utility or minimize the loss, or maybe I'll go ahead with this problem without short selling. So I have just held up the camera for a while and just wrote down this list of symbols. You might be wondering that I have suddenly written an inverse of this matrix. Positive semi-definite matrix doesn't mean that it should be invertible. So its eigenvalues are non-negative, and there could be a zero eigenvalue too. What we are now going to put in two important assumptions, and which are absolutely practical. Number A, assumption A says that this matrix, the variance covariance matrix, is positive definite. The variance covariance matrix is positive definite. And second, R hat is not a multiple of E. So if I write this in a much more clear way, then this I should write this as this inequality constraint. And so what does this mean? If you take this function, you take this function h1x, h2x, h1w, h2w. So the gradient here is r hat, the gradient here is e. If they are not multiple of each other, they must be linearly independent. So you are telling that the gradient are linearly independent. Let us see what this condition tells me. It tells me that if these two are linearly independent, so there are two constraints and they are linearly independent, and this is an n-dimensional thing. So the maximum number of linear independent constraints in a n-dimensional setup, in an n-dimensional space in Rn is n. So here two of them are linearly independent. If n could be 2 also, so that is fine, but n cannot be 1, right? Then this problem would be trivial. So this condition says that n is here always greater than or equal to 2. This is a very, very fundamental thing. So you are to do something of meaning in the securities market, you need to invest in at least 2 different assets. And then what does this mean? This means that, okay, if it is not positive definite but positive semi-definite, then things could be different. Positive definite means, so positive definite so matrix is positive definite if this means that but so this can happen. So only if it is 0, this would be equal to 0. So if you have non-zero allocation, this is always positive. But if it is just positive semi-definite, this would mean what? This would simply mean the following. This would mean that there could be a allocation omega hat such that so there could be non-zero allocation omega hat sorry. So there could be a non-zero allocation omega hat such that this inner product is 0. So which means that if it is just positive semi-definite, there could exist allocation omega hat, allocation of weights such that the risk is 0. So I will allocate in that way, I do not care about that. If my risk is 0 and I am getting that reward, so there could be a W hat which satisfies this and they give me 0 thing. So that is optimal. So that is exactly the thing I will do it. So means there could be the positive semi-definite assumption also leaves space for the existence of an allocation which is completely risk-free, 0. But in a securities market, no, nothing is free of risk. So these sort of things would never be allowed, that you cannot have a risk-free run in a securities market. That is why it's much more natural to assume this as positive definite matrix. And every positive definite matrix has positive eigenvalues, and the determinant is the product of positive those eigenvalues which is strictly greater than 0, and hence it is invertible. Now once that is done, and under these assumptions, of course the Karush-Kuntakar condition holds, naturally, and here what happens, one can guarantee a solution, and when this happens, this class of problems are now called strictly or strongly convex problems, and they have a unique solution over the set of constraints here. They form what is called a closed convex set. If these term looks Hebrew to you, please go and read some very basic optimization book. So you might be asking me, where is your probability and stochastics coming in? See, because already we have got into expectation and all those things, this is essentially some sort of stochastic optimization. But we would also like to stress that within next 3-4 classes, we will get into hardcore stochastic analysis, and our aim is to go and prove a stochastic approach to the Black-Scholes equation, the Black-Scholes formula, to derive the Black-Scholes formula without recoursing to a solution of a partial differential equation. That is essentially the goal. Okay. So now what we would do is that we would write down the result, that if what is the optimal solution of this problem, and that solution would be unique, right? We will write down the result now, and then we will try to analyze it. So now let us write down what is the solution of this particular problem. So here we consider only risky assets. We will talk about non-risky assets tomorrow, in not one of the last classes, but we are essentially talking only about risky assets. The first thing I want to tell you is that this and this, alpha, gamma and delta, are positive constants. Okay, and once that's you know that, then the solution of this problem is the following. Your solution, which I write as omega star, is a unique allocation. So under this situation, your allocation will be unique. You cannot have any other choice, right? So let us make that unique allocation. Of course, in the last example also you show that the allocation was unique given that rho bar. Of course, here rho bar, rho naught will of course play a role. So the allocation here is given as follows. So what I'll do is that, because just to save time, I'll stop the camera, write down the results and then explain to you. So here the solution W star would come to be this. We will see how it comes to be that. Lambda 1, the first Lagrangian multiplier comes to be this, second Lagrangian multiplier comes to be this. Each are dependent on the choice rho naught that you have made. So rho naught is truly the parameter of the problem. So if you change that, the solution changes. So you plug in these values, lambda 1 here and lambda 2 here, you get your unique solution. You put in here and then you take the inverse of this matrix, that's it. If it is uncorrelated matrix, then it's much more simpler, right? It looks, the W vector would look nice. Now how do I get the solution? Again, going back to the Karush-Kuntaker conditions, the Karush-Kuntaker conditions would actually give me this rho omega minus lambda 1 r hat minus lambda 2 e is 0. Of course, its next equation is e of omega is 1 and r hat omega is rho naught. Now I can put all this in the matrix form. If you look at it very carefully, I can put this in the matrix form, and in the matrix form it looks like a partitioned matrix R hat E transpose and R hat transpose, and here I would have W minus lambda 1 minus lambda 2. So, if you are just clubbing all this in the matrix form, and this would give me the 0 vector. Okay, I am not writing the 0 vector straight. So, I am writing not giving the 0 vector actually. The first thing will give me the 0 vector, then I will have the 1 and the rho naught. So, it will give me here the 0 vector, okay, and then it will give me 1 and then it will give me rho naught, right, n plus 2 vector. So, now if you do that, from the first equation it is obvious what you get. From the first equation it is obvious that sigma w is lambda 1. Okay, I will just write I think I have written it in a slightly different way. I have put the Lagrangian, I have put this as lambda 1 E minus lambda 2 R hat. It could be changed, okay, this equation can be changed. This I made a, okay, I had just, because in my writings I have just reversed this. I had actually this one EW equal to 1 and R hat W equal to rho naught. So, I have changed the lambda 1 will come with respect to this and lambda 2 will come with respect to this. So, Lagrangian multiplier for this is lambda 1 and this is lambda 2. So, if you look at this, this is nothing but lambda 1 E plus lambda 2 R hat, and then omega would be nothing but sigma inverse lambda 1 E plus lambda 2 R hat. So, your job now would be, once you know that, to find the remaining, that is all. So, your job would be to find lambda 1 and lambda 2. Now, how would I find the multipliers? So, I have got the omega, so W, so I have E transpose W is equal to 1, or E inner product W is equal to 1, and I have R hat W is equal to rho naught. So, what does this give me? It will give me, if I write this, it will have, I will put W, I have now got W star, so that I will put, so it will sigma inverse lambda 1 E plus lambda 2 R hat, that is 1. So, these are two components of a vector basically, or it can be written in the form of a matrix, and then I have R hat sigma inverse lambda 1 E plus lambda 2 R hat. This is rho naught. Actually, if you club this whole thing into a matrix form, then one can easily write the following, that lambda 1 lambda 2 can be written as E transpose R hat transpose sigma inverse E R hat, this whole thing inverse, because this is a matrix, please remember that, into 1 rho naught. So, once you do that, once you can write this, then you can use these formulations. Actually, you will see this formulation will come. Just let me take this. So, what will come here? E sigma inverse lambda 1 E plus sigma inverse lambda 2 r hat equal to 1. So what I am getting? Lambda 1 E sigma inverse E, right, plus lambda 2 E sigma inverse r hat, and that's equal to 1. But either you write it in this form and immediately do it using the matrix thing, which is a very compact form. So those who feel uncomfortable to put it in this form, just go and do it directly and write two equations. So this is nothing but alpha and this is nothing but beta. So lambda 1 alpha plus lambda 2 beta is equal to 1. So similarly in the second case, you will have lambda 1 beta, and then if you look at this, it will give you lambda 2 gamma equal to rho naught. So just solve this out for lambda 1 and lambda 2, right. So once you solve this out, you will immediately get these answers, right. So don't you worry. So once you have done this, you are through. So you have now known how to actually handle the problem. So thank you very much for listening. So tomorrow we are going to, the next class we are going to talk about how risk and reward actually interacts. We will look at it in a much more deeper way. Thank you very much.